All right, everyone, welcome back to AI Paper Podcasts. Today, we're diving into a paper that's making waves. MoM, linear sequence modeling with mixture of memories.
Yeah, this paper is tackling a huge challenge in AI right now, making powerful language models more efficient, especially when dealing with tons of text.
What's fascinating is that the researchers took inspiration from, well, the human brain. Let's give everyone a quick summary of the key takeaways.
Okay, so MoM introduces multiple memory states inspired by how our brains use theta and gamma oscillations to, handle multiple memories without them interfering. This significantly increases memory capacity and reduces interference in linear sequence models.
Like giving AI a much-needed memory boost.
Yeah, exactly. MoM also uses a router network, kind of like a traffic controller, that directs information to specific memory states. This enables parallel processing, which means faster training A and D inference, and the performance, it blows other linear sequence models out of the water, especially on tasks that need recalling information from long stretches of text.
So not just faster, but actually better at understanding and remembering. That's amazing.
And get this, MoM even rivals transformers, those AI heavyweights, particularly in common sense reasoning tasks.
Wow, that's impressive. Now let's unpack the details and see what makes MoM so groundbreaking. Why is this such a big deal?
To understand that, we need to look at the limitations of traditional linear sequence models.
Okay, so what's the issue with how these models handle memory?
So traditional linear sequence models, while faster than transformers, struggle with memory capacity and interference. Imagine they try to cram all information into a single fixed-size memory. It just doesn't scale well.
Like fitting an entire library onto one shelf, bound to lose something.
Precisely. Yeah. And that's where the inspiration from the brain comes in. Our brains can store and access multiple memories without mixing them up, like different compartments for different types of information.
So MoM tries to replicate that in AI.
Yes. Instead of one massive memory bank, MoM uses multiple memory states, each like a specialist handling a specific type of information.
Like having a team of experts instead of one person trying to know everything. How does it decide which information goes where?
That's where the router network comes in. It's like an intelligent traffic controller directing information to the right memory state based on the content and context.
A librarian who knows where each book belongs.
A great analogy. The router network is crucial, ensuring each memory state focuses on specific information, preventing overload and minimizing interference.
This is already sounding way more efficient. But let's look closer at those memory states. How do they actually work?
Each memory state, in a way, functions similar to transformers, but with a key difference. They use linear projections to create their own sets of keys and values for the information.
Hold on, quick refresher. What are keys and values here?
Keys are like labels to identify information, and values are the actual information. So each memory state has its own set of labels and information specific to its inputs. Importantly, each one has its own storage for these key value pairs.
So no more overwriting or conflicts. Each memory gets its dedicated space.
You got it. But we also need to update these memories with new information, like our brains constantly learn and adapt.
Information's not static, it's dynamic. How does MoM handle that?
It uses a mechanism called a gated delta net. It's like a smart note-taking system, adds new information, but also forgets less relevant details.
So our AI is learning to prioritize important information, just like us. But we have all these separate memories. How does MoM make sense of it all and give us an output?
That's the mixing and mixture of memories. The output comes from querying a weighted combination of all the memory states.
Like each memory state votes on the final answer, some votes way more.
Exactly. This mixing gives MoM a broader understanding of the entire input, even long and complex ones, like a panel of experts reaching a decision.
Incredibly powerful. But complexity often means less efficiency. How efficient is MoM? Faster than traditional linear models, but is it as fast as those efficient transformers with flash attention?
MoM is designed with efficiency in mind. Those separate memory states we talked about, they're not just organized, they allow parallel processing.
So processing multiple pieces of information simultaneously, that speeds things up.
And MoM has a shared memory to handle those long-range dependencies across the input.
Explain that in simple terms.
Think of it like a central hub connecting all the individual memories. It allows MoM to track relationships between pieces of information far apart in the input.
A master index keeping everything organized and connected.
Right. And for maximum speed, MoM uses chunk-wise parallel processing. Basically, it breaks the input into chunks and processes them at the same time. So training and inference are much faster.
So an AI that's not just smart, but also super fast.
Precisely. This combination makes MoM a game changer for various AI applications.
Which brings us to applications.
Yeah.
Where could MoM shine? Where could it make a difference?
Well, MoM's perfect for tasks that need both speed and accuracy. Think real-time language translation, analyzing tons of data, or even summarizing complex documents like legal or scientific papers.
Areas where AI needs to understand and process a lot of information quickly? Sounds like almost every industry these days.
You could say that. And to understand how these design choices impact performance, they did some performance tests and ablation studies.
Let's dive into those. How did MoM perform compared to other linear models and, of course, the gold standard, transformers?
On tasks that need strong recall, like those question-answering scenarios, MoM blew other linear models out of the water. The difference was substantial.
Incredible. And compared to transformers, how did it hold up?
Remember how we said MoM could challenge transformers? Well, even in common-sense reasoning tasks where transformers usually dominate, MoM performs surprisingly close.
A remarkable achievement. But it's not just about benchmarks, right? It's about how different design choices affect performance. That's where those ablation studies come in. For those who don't know, ablation studies are like experiments where you tweak parts of the model to see how the results change. What did these studies reveal about MoM?
They provided insights into the balance between complexity and effectiveness. For instance, increasing the number of memory states initially improved performance, but only to a point.
So, more memory states aren't always better.
Right, too many. And the model becomes too complex to manage. Like juggling too many balls, you'll drop some.
Makes sense. What other insights did the studies give?
They confirmed the vital role of that shared memory. Removing it caused a performance dip, especially on tasks with those long-range dependencies.
Like removing the central nervous system. Things wouldn't connect well.
Exactly. The studies highlighted how important that shared memory is for MoM to understand those long, complex sequences.
Really insightful. This emphasizes why ablation studies are important, understanding how things work, what are the strengths and weaknesses, to build even better AI.
Absolutely. These studies give us valuable insights into the inner workings of these models, helping us refine our understanding for further advancements.
Now let's think bigger picture. What does this mean for AI's future?
It's a great question. One thing's clear, MoM isn't just a new model. It shows us the power of drawing inspiration from nature, especially from the human brain.
Makes you wonder what other secrets of human intelligence are out there, waiting to be applied to AI. Maybe MoM is just the beginning.
I completely agree. Now let's shift our focus to those real-world applications. Where do you see MoM making a difference soon? One area that jumps out is real-time language translation. Like imagine a world without language barriers. We could talk to anyone, anywhere, regardless of what language they speak. MoM's speed and accuracy could make that happen.
That's a powerful vision, breaking down barriers, connecting people, making the world a more inclusive place.
Exactly. And it's not just spoken language. Think about all the written information generated every day. Emails, social media, news articles, research papers. MoM could unlock insights from all that data.
So analyze customer feedback, track trends on social media, or personalize education based on learning styles.
Precisely. And AI-powered assistants, think about that. Smarter assistants that can handle complex tasks, not just scheduling meetings, but maybe helping you write better code or even compose music.
Now that's exciting. AI that not only does tasks, but helps us achieve more.
Right. MoM's ability to handle long texts, understand complex relationships, and reason logically makes it perfect for tasks needing deeper cognitive processing. Like imagine a super intelligent partner, always a step ahead, offering suggestions.
I can already see myself collaborating with a MoM-powered AI on my next project. But back to reality. Where do you see MoM making the biggest impact soon?
I think it'll be in fields that are already data-driven, like healthcare, finance, and research.
Yeah, I could see how it could revolutionize them. Analyzing patient data for personalized treatments, detecting fraud in real time, or even speeding up scientific discovery by analyzing huge data sets.
Exactly. And it goes even further. MoM could even help address big challenges like climate change, poverty, and inequality.
Wow, I see it now. Using MoM to analyze climate data for better strategies to fight climate change, or economic data to design policies that reduce poverty.
The possibilities are huge and exciting, but we need to stay grounded in the research. MoM is still new, and many challenges need to be tackled before widespread use.
Right, AI is always evolving. What's cutting edge today might be normal tomorrow. So what are some of those challenges?
One is developing better router networks. The router directs information to the correct memory state, and as models get more complex, routing becomes even more critical.
Like a traffic controller managing an increasingly complex network of roads.
Precisely. As MoM models get more complex, we need routers that can handle more nuanced information flow, ensuring that information is routed efficiently and effectively.
Makes sense. Any other challenges?
We also need more robust and interpretable memory update mechanisms. These AI models need to learn effectively in a way that we understand and trust.
Right. AI needs to be transparent and accountable. We need to know how decisions are being made and make sure those decisions align with our values.
Absolutely. We want powerful but also responsible and ethical AI. It's crucial as these systems become more sophisticated.
It points to a future where AI is not just a tool, but a partner working with humans to solve problems and build a better world.
I couldn't agree more. Models like MoM, inspired by the human brain, will play a vital role in shaping that future.
Now let's focus on those performance results, especially those tasks that really test a model's ability to remember and connect information from long stretches of text, those recall-intensive tasks.
Yes, like answering complex questions from a massive document or summarizing a long research paper. Tasks needing the model to access and combine information from many sources.
And on those tasks, MoM did significantly better, surpassing other linear models. We're talking a big jump in accuracy and completeness.
Precisely. Now, about those comparisons with transformers, MoM held its own, especially on common sense reasoning tasks, even when compared to transformer models with flash attention.
So MoM is faster than traditional linear models and can reach a level of sophistication we thought only transformers could.
Exactly. And to really see the impact of those multiple memory states, they had MoM compete against a version of itself with a single bigger memory, like comparing a giant warehouse to specialized storage units.
Interesting. So it's about how the memory is organized and accessed, not just size. What do they find?
The MoM with multiple memory states consistently did better. This shows that dividing memory into specialized states is key to MoM's success.
Almost like those specialized memory states allow MoM to understand information better, similar to different areas of our brain specializing in different functions.
That's it. It all comes back to bio-inspired AI, using nature to design more intelligent and efficient systems.
MoM is a perfect example of how that can lead to amazing results.
Absolutely. It challenges the idea that bigger models are always better, showing that we can achieve a lot with models that are also efficient.
For a long time, the focus in AI has been on bigger and more complex models. But MoM shows us that there's another way, a way that prioritizes both performance and efficiency.
Yes. And the shift in focus could change AI, making it more accessible, sustainable, and beneficial to society as a whole.
Before we finish this part of our deep dive on MoM, let's look closer at those ablation studies. What happened when they changed the number of memory states? Did they find a perfect number?
They found that more memory states meant better performance at first, but only up to a point. Too many, and the model became too complex and hard to manage.
Like the saying, too much of a good thing can be bad.
Exactly. Finding that balance between complexity and efficiency is key.
And what about that shared memory? Did the studies show anything specific about its role in handling those long-range dependencies?
They showed that removing the shared memory had a big impact on performance, especially with those long-range dependencies.
Like removing the connections, the model can't make those links between information far apart.
Precisely. Those studies highlighted the importance of shared memory for MoM to understand long and complex information sequences.
This is really insightful, and it shows why these studies are important. It's about understanding how these models work, their strengths and weaknesses, so we can build better AI.
I agree. These studies help us understand how these models work, leading to more advancements.
Now let's think about MoM's future. What are the broader implications of this research for AI?
MoM is more than just a new model. It changes how we think about AI. It challenges the idea that bigger is always better. We can achieve great results with efficient models, too.
That's a message that resonates with many AI researchers. It's a call to focus on developing AI that is not only powerful, but also accessible, sustainable, and beneficial to society.
Exactly. MoM opens up new possibilities for research and development, leading to a new era of intelligent machines that are powerful and responsible.
Well said. Now let's talk about another important aspect, the ethical considerations.
Yes, that's important. As AI systems become more powerful, we must consider the ethical implications and ensure responsible use for humanity's benefit.
We need to think carefully about how MoM and other advanced AI could be used and put safeguards in place to prevent potential harm.
I agree. For instance, we need to make sure these models aren't used to create bias, invade privacy, or manipulate people.
These are critical points. We need a thoughtful discussion about AI ethics.
Absolutely. We need to be both enthusiastic and cautious about AI, making sure these technologies create a just, equitable, and sustainable world.
That leads perfectly to our final topic for today: potential risks and downsides. What should we be careful about as we develop and use MoM-based AI?
That's a crucial question. One risk is the concentration of power. As these models become more powerful, we must ensure they aren't controlled by just a few.
We need to ensure AI benefits everyone and doesn't make inequality worse.
Another risk is misuse. Imagine someone using a MoM-powered AI to create very realistic fake news or propaganda.
That's scary. We need safeguards to prevent that.
Definitely. We need to be proactive about these risks and have open discussions about AI ethics.
Well said. That's a perfect way to end our discussion about MoM's potential risks.
You know, one really exciting thing about MoM, it's not just a one-off innovation. It's like a spark. It could start a whole wave of new research in AI, making it both efficient and powerful.
Okay, so how does MoM push things forward? Give us a peek into the future of AI research.
Well, MoM makes us rethink this idea that bigger models are always better, that trade-off between complexity and performance. For a long time, we thought bigger was the only way.
Right, like a race to build models with billions, even trillions of parameters.
Exactly. But MoM shows we can get amazing results with models that are much more efficient. So we could have AI that's not just powerful, but also accessible and sustainable. A win-win.
So AI that could even run on less powerful hardware, maybe even our phones.
That's it. And think about what that means. It could democratize access to AI, making it available to researchers, developers, anyone, even if they don't have huge computing power. That's huge for fields like healthcare, education, or even conservation.
I see what you mean. Those fields could really benefit. So are you saying we could see MoM-inspired models used for things other than language processing, like image recognition or even robotics?
Absolutely. This idea of managing memory efficiently and processing things in parallel, that's applicable to lots of different AI applications.
That's pretty exciting. But are there any challenges, roadblocks researchers might hit as they explore these new areas?
Well, one challenge is coming up with even smarter router networks. Remember, the router's job is to send information to the right memory state, and the more complex these models get, the more important that routing becomes.
Right, like having a really good traffic controller to make sure everything runs smoothly.
Exactly. As these MoM models get more complex, we need routers that can handle lots of information that's constantly changing, and make sure everything's routed efficiently.
So a router that can learn and adapt as the AI model learns new things.
That's exactly it. And another challenge is developing ways to update memories that are more robust and easier to understand. It's not just about the AI learning, it's about us understanding how it's learning and trusting that process.
Right, AI needs to be transparent and accountable. We need to know how it's making decisions and make sure those decisions align with our values.
You got it. We want AI that's powerful, but also responsible, ethical AI. That's crucial as these systems become more and more sophisticated.
It all points to a future where AI isn't just a tool, but a partner, working with us to solve problems and make the world a better place.
Couldn't have said it better myself. And models like MoM that take inspiration from the human brain, those are going to be essential in shaping that future.
Well said. It sounds like we've reached the end of our deep dive into MoM.
Yeah, it's been a really interesting journey exploring this model and all its potential.
To everyone watching, we hope you found this deep dive into MoM insightful and thought-provoking.
As always, we encourage you to check out the full paper, get into the nitty-gritty details.
MoM is definitely a big step forward in AI, and we can't wait to see how it shapes the future.
Absolutely. So until next time, keep exploring, keep innovating, keep pushing the boundaries of what AI can do.
That's it for this episode of AI Paper Podcasts. We'll see you next time.